Hello everyone, we're ready to start. So this week we continue from home and probably for a number of weeks. So I hope you are comfortably installed and we'll try our best to have good lecture and good conditions for all of you in these conditions. The topic today is link state routing. Let us start with a few general statements about routing. We will talk about link state routing, which is for us synonym to OSPF, which is the most widespread routing protocol used in enterprise networks and in cellular operator networks today. The word routing has several meanings. In this course, I will try and be consistent and use the word routing in the sense of a routing protocol, like we will discuss now. But if you read on the internet pages on TCP-IP, often people use the word routing as a synonym for IP packet forwarding. So a device that is a router routes packets. So if you decide to set up your Linux machine to do IP packet forwarding, then some people will call that, many people will call that routing. Okay. Of course, what we need to remember is in our context, that's a bit different. The goal of a routing protocol is to set up the routing tables. We have seen that routers need routing tables where they do longest prefix match. And in the labs, we set them up manually. But of course, we want to do that in a smarter way. In fact, setting up routing tables manually is not an option for most cases because you want to be able to do that remotely. So there's a chicken and egg problem. How do you remotely access information or change information on a router if you don't have a means to go to this router already? So this is what a routing protocol will do. There are many ways of doing routing protocol, and historically the first routing protocols were using distance vector that we will see later in the course. But today most use link state and path vector that we will study. Link state is OSPF, path vector is BGP. The principle of a link state routing protocol is very simple. We could even say it's simplistic. All routers in one domain have a map of the entire domain. So link state is Google Maps, if you want. This map is, of course, a network map, so it means it is a graph where nodes are routers and where links have a cost, where, like we saw for the spanning tree protocol, the cost reflects how much we would like this link to be used. So if we want a high-speed link to be used more than a low-speed one, we'll give a higher cost to the low-speed link. Routers compute next hop to destination. That's the goal of a routing protocol. And the classical way is by computing shortest paths based on this graph that they have. They can compute shortest paths. This is the default in the best effort internet. In enterprise networks, where we can do what is called quality of service, we can choose paths with different criterions than being the shortest. For example, we might want a path with the smallest delay if we're interested in having interactive video and audio, or with the largest available bitrate, the largest available bandwidth, if we're interested in doing fast transfer. And those two might not be the shortest in number of hops. So this is used in OSPF. We'll see also other methods where this is used. There's another method that was historically the first one. It's called distance vector. With distance vector, things are a bit smarter if we want. Instead of having link state is in some sense completely brutal. You have a complete map of the network. Every router finds a way to have this complete map. And then in order to know which way to go to somewhere, you do a shortest path computation. This is what Google Maps does for you when you use it to find an itinerary in your car or on your bicycle. Distance vector is smarter. With distance vectors, all routers in one domain know much, much less. They don't need to have the entire map. They only need to know who their neighbors are. So that is something you need to know for any routing protocol, plus the distance to all destinations. The distance to destination is some very limited information. You all anyhow must have a routing table. So with distance vector, the only additional information we need is in the routing table, not just how we go there, but what's the distance to that. So this is compressed information, much, much less information. You know only locally what you have to. Then routers inform the neighbors of their own list of distances and their costs to all, the list of destinations and the distances they have to all these destinations. This is called the vector of all distances. And then there's a distributed protocol called Bellman-4 that is able to exploit only this information to discover shortest paths. So that is a radically different method. This is the same method that is used by the spanning tree protocol when a bridge computes what is the path to go to the route, to the root of the spanning tree. They use this same method here, which is very, very compressed, very lightweight. So it is something that was historically very interesting when devices were had very low memory and small processing capability. Path vector, so we will see distance vector at the end of the course. It's methods like RIP, well-known protocols like RIP use this method. Path vector is a radically different story. With path vector, every router knows its neighbors, but also explicit paths to all destinations, and it's used for BGP. We'll do an entire lab on BGP, so we'll speak about that later. There is another method that we will not discuss in detail, but is important to know. It's very simple. It's called source routing. Source routing was used historically in token ring bridges, and it is used in ad hoc network. Ad hoc networks is a terminology that is used when you, for example, have an emergency response situation where you deploy on the field a number of boxes that you want to be as routers, and you want to create a mesh without much, you want to create the mesh on the fly. So DSR is, for example, used by companies like Caterpillar when they do a network by all the machines that are working out on the field. The way it works is as follows. Source routing means that the path that is to be taken by a packet is computed by the source. This is what source routing means. I mean, the route is computed at the source and is written in the packet. There are different ways to do it depending on which protocol you use. If you use IPv6 with DSR, for example, you would use an extension routing header in the IP header. And let's take an example. A has a packet to send to B. Through some mechanism, A has found that a good path or possible path to B is the path that is written here. A, R1, R2, R4, and B. Then A will write as destination address not B, but the next hop, which is R1, and in the routing header, this is an extension header, will write the rest of the route, R2, R4, RB. Then this packet will be sent by A. The rest of the IP layer will see destination R1, so it will send it to R1 using ARP to find the MAC address of R1, and will send it to R1. When R1 will receive it, R1 sees that there is an extension header and will not conclude that the packet is destined to R1, but since there is an extension header, R1 will look into what is the next, the rest of the route, and finds that there is R2, R4B. So R1 will modify the IP header, will put R2 as the next destination, the destination field of the IP address, and will remove R2 from the destination header, etc. So the packet will be sent by R1 to R2. R2 will do the same, and the packet will be sent by R2 to R4, next destination R4, and R4 will send it to B. So B will receive this packet without any destination header, so B knows it is destined to itself. So this is one simple method. Of course, we don't say how A will discover the path. This is another story. So how can A discover this route? In this type of environment, the network is typically small and changes very often. So one method that is used is simply to flood explorer packets. So the first time when A talks to B, A will simply flood a message. Flood means it's sent to all the neighbors of A. So it will be broadcast to the entire network. A will flood a special explorer packet to R2 and R1. R1 will flood them in return. So that will create potential loops. The loops will be broken because the explorer packet accumulates the route. So when A sends it to R2, R2 will write into this explorer packet the path that has been taken so far. And if there is a loop, then it's detected by examining the path that is taken. Of course, that will create an exponential number of packets by all the possible loops that exist in this network. So a large number of those packets will be created, and many of them will be received by B. B will decide which of these packets it prefers. For example, very often B will simply take the first one by the decision that if it comes first, that was the fastest path. So B will see in the packet a valid path from A to itself. For example, in that case, the path that was chosen here perhaps was the first one that could reach B. So B will read the content of the explorer packet, reverse the path, and send the information to A, and now A has the source of information. This is how ad hoc networks will typically do it. What I've shown here is called strict source routing. What is strict is that the route has to be followed strictly. That means that the next hop is really R1. If R1 is not on link with A, for example, because this is an ad hoc network and the nodes are moving and the connection from A to R1 is lost, that will not work anymore. So the connection will be broken. This is strict source routing. In the internet, there's another form of routing which is used, which is called loose source routing. I said in the internet, but this is used not in the global internet, it is used in enterprise networks, in internet service provider networks, and in data centers. Here, the idea is a bit different. There is also a routing header. It looks very similar. The type of this routing header is different, so routers know it's not the same routing header. It's a loose source routing header. And here, the idea is that what is written here is an indication. This is a via. So here, A wants to go to B, but A says, I must go first to R4. But R4 does not need to be on link with A, which means there must be another mechanism, another routing protocol, for example, like OSPF, that allows us to go from A to R4. So loose source routing is a way to force some routing decisions that do not follow what the routing protocol says. So here we're saying in order to go to B, first go via R4, R2, and R5. So otherwise, this is the same. So A will send this packet to R4 using its routing table. R1 and R3 will use their routing table to send it to R4. R4 receives this packet, but sees that there's an extension header. So we'll look at the extension header and see, oh, it's not TCP, it's a routing header. Therefore, it's not for me. I have to send it further to R2, which will do the same, etc. This is used for what we call traffic engineering. That allows us to have fine-grained control of traffic. If you want to force traffic to not, some kind of traffic to not go via R2, which might be the normal, the default route that A has to go towards B, then you can supersede the decision of the routing protocol in this way. This is used for traffic engineering, for separating flows, also sometimes for separation of customers, or also, as we will discuss, perhaps you want to force all packets to go via R2, because at R2, you will do some security functions, for example, filter all the traffic, and you want to make sure all traffic goes, sorry, not R2, but perhaps R4 is the node that does this security measure, so you don't want to bypass R4, for example. So loose source routing is used also in data centers, where we want to have more fine-grained control of the huge switching fabric that is made by all the distributed routers and switches. In data centers, people use even sometimes something called segment routing, which is an extension of source routing where the extension header gives not only where you have to go next, but also might indicate some processing instructions. So you go a bit beyond simply routing and you give to the router the instruction, for example, to R4, the next hop should be R2, but perhaps you want to give an instruction here on some processing you want to apply to this packet. For example, typically this is security processing. You want to do deep packet inspection on this packet, which will slow it down, but is perhaps something you want to do because you have a security problem. Voilà, this was a very quick and superficial overview of all the different routing methods that exist in the internet. Now we will dive into one for which we will do also a lab, which is OSPF. OSPF stands for Open Shortest Path First. Shortest path first alludes to the fact that it computes shortest path, like not surprising, and open because this is open software. It was it took some time to become popular. It emerged in the 90s, and now it's the leading protocol for single domain. Single domain means EPFL, for example, a switch. When we go across domains, we'll use something else that we'll discuss later. It uses also multiple areas. So inside the domain, you can have multiple areas. We'll talk about this in a few more minutes. Right now, let's assume there is a single area. So inside an area, every router has 3 databases. And so remember, it uses link state. So the principle of link state is that every router has a complete map of the entire network. This map is built from first the local information, that's the interface database, that is a router knows all the interfaces it has and all the subnet prefixes that are attached to it. So this is learned by the configuration. We've done that in the lab. We do IP address show, for example, and then we have the information. So OSPF will use this information. Plus, it also needs to know who are the neighboring routers. So a router that runs OSPF must be configured to allow neighbors to talk to him or to her using the hello protocol and also some cryptographic means that we will describe a bit later. So the hello protocol will take the role of discovering neighboring routers, and detect failures. If neighbor hasn't said hello for a few seconds, we assume it's down, and then we will reconstruct routes around this failure. So this is the second element. And then a global information is built from that and distributed, replicated, in fact, in every routers, which is called the link state database. This is the network map. So when 2 routers become neighbors, they first synchronize their link state database. Typically, things are asynchronous. You don't bootstrap a network exactly at the same time for all routers. So some routers will have been running, have some snapshots of the state of the network. If a new router connects to an old router, then the new router, the first thing it will do is to learn from the old router the network map that it has. Because remember, the goal is that the link state database is replicated in all routers. This is called synchronization. Once a router is synchronized, it will maintain the link state database by, hello, Jean-Marie, somebody is drawing on the screen, right? Interesting. So the link state advertisement are the updates to the link state database. If anything changes, and things often change in a network of routers, then new messages are sent, and those messages give the new information. So This information is the local information. It's the attached network and the neighboring routers. Those pieces of information, the LSAs, link state advertisements, are flooded and stored by all routers, and this is what allows all routers to have the replicated database. Of course, if we flood, we need to be careful. So they contain a sequence number. The sequence number is used to avoid loops. When a router sees a message, it keeps a memory, it updates its database, and when it sees a new message, if the sequence number is the same or older than the existing one it has in this in its database, it will not reflood it to other routers. Also, there is an age to make sure that old information doesn't stay forever, and the age is used to resend LSA and flush invalid values. But most of the time, as we will see, there are other mechanisms that are used to propagate changes. Let's see an example here. Here I have a small network with 1, 2, 3, 5 routers, a number of links. For OSPF, like for most routing protocols, we make the distinction between point-to-point links. So the zigzags here are showing point-to-point links, and the thick lines here are showing shared media links. So we say shared media. In reality, for us, most likely it means a switch, a network of Ethernet switches here. So it's a LAN, a local area network. So this is the starting point. At the beginning, if hypothetically all routers start at the same time, the only thing they know is their interface database. For example, router B knows that it has a prefix N3, that's an IP prefix here. It has, it will say what is the type of this, so it's a point-to-point link, Ethernet, and also it will say whether it is a stub or not. So what is a stub network? A stub network is a network that does not connect, is a link or a network that does not connect to another router. So this here goes nowhere. It's a dead end. So if it's a dead end, we don't need to have a cost for them. We will see that we can optimize the performance of the route computation by first ignoring all the stub destinations, because if somebody wants to send a packet to N3, it has to send it to B first, because there is no, N3 is not connected to anything else. So all routers need to compute only their distance to B and the path to B, not to N3. So N3 will be visible, but will not be used for shortest path computation. In contrast, N2 and N4 are marked as point-to-point links, and here we must give them a cost. So here B has decided to give them a cost of 100 here. So each router has this information here, and this information needs to be configured with the router configuration. There's no distributed protocol to do that. When you set up your router, you have to write this in each of your routers. Then routers will flood this information, which means B will simply send its local information to all its neighbors. So it will not send it to N3 because N3 is a stub network. It will send it to C, and it will send it to A. So the same information will be sent to A and C. It is simply a local copy of what B knows. This message will be received by C, and it has a number. It will be resent by C to A, but A will not re-forward it if A receives a message from C before. It's also possible that A manages to send this message back to C before, in which case C would not flood it, send it back to A. And at the end, after this very simple mechanism, which is, it's very simple, it's not very efficient in terms of bandwidth and computation. This is why this method became popular only once processors and memory became powerful. So at the end, all routers will have the same information, which is shown here. That's the link state database, which will be the same in all 5 routers. Of course, they don't have a graph. They have a textual representation of the graph, which is written here. So we've seen what B has sent. If we explore what C and A has sent, we see a small difference. We see that C has sent its topology data, its local database, and the local database of C is saying that C is connected to N1, and N1 has a field called designated router. Designated router C means that here we have a LAN, a local area network. Very often on a local area network, there will be more than 2 routers, or there can be more than 2 routers. So if there would be 3 or 4 or 5 routers in this LAN, then we will not have everyone sent to everyone. We will not have this n-square communication. Instead, one of the routers in this network will speak for the LAN and will take the role of designated router. So when A and C discover that they are on the same LAN, they quickly elect one of the two, typically the one that has the largest identifier, will become the designated router. So here it is C that became the designated router. So we see that here. That means that C has to speak for network N1. So C will send to anybody, to everyone, another link state database, which is, I am network N1, I am an Ethernet, I have a cost of 0, we'll see why, and I have routers A and C connected to me. So router A will simply say, I am connected to N1, designated router C. So to find the complete map, we need to combine everything. So this is how OSPF works. I mentioned link state advertisement. In fact, there are many types of link state advertisements. We've seen the most common one, the router LSA, but there are other ones. The most interesting one that we will see a bit later are the ones that are used in the context of BGP when we connect to other networks, or also in the context of multi-area network. If you have multiple areas, we'll see that there are other type of topology database information. We will come back to that in due time. Plus, there is a large number of special things that we will also discuss at the end. Now, let's take the same example, and let's assume that router F now pops up. So router F that was connected to N7 and N1 perhaps was down, was not yet started. So now, if we start now router F after starting those 5 first routers, what will happen? This is, in fact, the common case. It's very uncommon that 5 routers start exactly at the same time. But to simplify the story, I showed it. So the first time that F will do is discover the adjacent routers. So F will send the hello protocol on N7 and N1. We'll discover that there's E, C, and A. We don't know whom F will discover first, so it will discover one of those first. For example, it might talk on this interface here, and C will respond because C speaks for this network here. So F will discover that C is a designated router on this Ethernet, and therefore F will copy the database of C. This is called the synchronization. Then, probably not so much later, F will talk to E, and F will compare the database that it has copied from C with what E has, and probably they are the same, so the synchronization here is over. And from this point on, F will start flooding the information that it has, which is essentially saying this: I am connected to N7 and to N1, so this information will be added by F. E also will see something new. E will see now on N7 I have something, so E will add some new, change its LSA, so there will be an update of the LSA of E that will be flooded to everyone, because now there's a new neighbor. Similarly, C, that now speaks for the network N1, will send an update of the state of network N1, because now it is N1 that is connected to F. So those are the changes that will occur. The things in red correspond to new messages that will be flooded by everyone in the network. And after a number of repetitions by everyone, all routers will have this new information. This is how the flooding works. Now, this is in reality how OSPF views the graph of the network. We've seen that shared medium networks are viewed as nodes. In fact, we've seen that C speaks for N1. So we'll have a graph where those nodes also are virtually present. And when we add virtual nodes, we add typically, not always, but we add a cost of 0 from the node to the router here, to make sure that the cost from E to F, for example, is exactly what E and F think that they are doing here. So this is the graph that will now be viewed by OSPF. And on this graph, OSPF will compute the shortest path. A few practical aspects that we'll discover in the lab. OSPF doesn't use TCP or UDP. It is directly sent over IP. So it is a protocol type or a header extension for IPv6. It's the protocol 89 in decimal. In hexa, it is 59. So this means the OSPF protocol. So since it is not using TCP, it needs to manage reliable transmission. It might be that a packet is lost on the path. For example, if there are switches between two routers, the switch might lose some of the packets. So very much like we've seen with the stop-and-go protocol, OSPF uses ACKs and timers. Whenever a packet is sent, OSPF expects an acknowledgement, and after some timeout, if the acknowledgement doesn't come, it will send it again. For every packet that is sent, whether it's a repetition or whether it is a packet originated by this node. So it does store and forward. It doesn't do end-to-end retransmission. Here it makes sense to do store and forward because every OSPF node is expected to have all the information here. So it's not just storing and forwarding for the purpose of serving the destination, but we also want to have the information locally. There are multiple versions of OSPF. We will use OSPF v3 that supports IPv6 and also supports networks that have IPv6 and IPv4, and there was an older version that used only IPv4. OSPF has identifiers for routers, which historically were IPv4 addresses. So now they are no longer IPv4 addresses, but they have the same format. They are 32 bits. And we'll talk about the areas a bit later. So with OSPF, every router has a map of the entire network. On this map, the routers will compute shortest path here to every destination from self. So the problem is now a graph theoretical problem. I have a graph and I want to compute the shortest path from a given node to all other nodes. For this, there is a well-known algorithm, Dijkstra, which is the best known algorithm in terms of complexity for the problem of shortest path that is posed in these terms. We will see that if we pose the problem in different terms, for example, if we want to do it distributedly, in a distributed way, then we will use other algorithms. But if we do it centrally, when I say centrally, there is not a central node that computes everything, but there is a central operation done by every router. So every router has the entire database and computes routes based on this entire database, unlike what will happen with distance vector. Paths are computed at every node. They have the same database, but of course the paths are not the same because the roots of the paths are self. Every router is interested in knowing how do I go from myself to every destination. So every router will solve a different shortest path problem. The flooding and the synchronization of databases guarantees that there will not be persistent loops. So every router will compute a path, and the shortest path, of course, will be free of loop. It might cause problems in the interim periods where things are changing. For example, if the topology is changing because a failure occurred, of course, there might be temporary problems. We'll talk about that a bit later. Here is one version of Dijkstra. This is perhaps the simplest version in the context of OSPF. This is the algorithm. So it's done at one node. I call it node 0. So the nodes are 0 to n, there's n plus 1 nodes. And we consider that this node is node 0. The input of the algorithm is the cost of every link from I to j. This is done by the interface database and propagated to everyone. So we have it from there in the topology database. And then we have a working set, V, which is the set of nodes that have been visited so far by the algorithm. And predecessor of I is at this current stage of the algorithm, is the predecessor of I on the route from 0 to I. M of j is the estimated distance from a node 0 to some node j or I. So here is how the algorithm works. So at every step, it adds one node to the working set, and it is the node that, based on the information we have at this stage, is the one that is the closest in terms of distance here. And the magic of this algorithm is that we do it in this greedy way. At every step, we add one node, we estimate the distance to this node, and this distance will not change. It is the final distance. So it is an example of a greedy algorithm that works. Normally, if you do greedy things, you are not optimal. We'll see that with Bellman-Ford used in distance vector, things are different. At every iteration, you have an estimate of the distance, but the final estimate will change, whereas here, it doesn't change. I think the simplest is to explain it on an example here. So here I'm showing a simplified version of the network we had before, and we are at router A. So this is the initial view of that the router has. So we have the topology database, so we know the graph. Here, to simplify, I assume there is no intermediate networks, and the link costs are the same in both directions. And the initial value of the algorithm says that M of A, remember M is the estimate of the distance at this stage of the algorithm. And for self, the distance is 0, of course. And for all other nodes, it is infinite, because we know nothing at the beginning. And we have added the working set is empty. In the first step, I add the node that is the closest based on the information I have. Well, all nodes are at infinite distance except A, so of course I add A. So at the first step, I will add A. This is what I do here. So say first step, this is step 0 of the algorithm, k equals 0. Then I've added A, which is shown in a different color here. And at the same time, what the algorithm does is, when I add one node, is update my estimate of the distances. If I know A, I can know at least an estimate of the distance to all the immediate neighbors of A, which are B, C, and F. By doing a calculation, I will compute the distance from self to A, which is 0, plus the distance of going to B via this link, that gives an estimate of 100. If I go to C, I have an estimate of 10. If I go to F, I have an estimate of 10. So those are the three estimates I can give at this point of the distances to B, C, and F. So I keep those estimates here. I keep not just the estimates, but also the route. The route is given by the red arrow in terms of data structure. It will be the predecessor. I have put an arrow from A to B. That means B, the arrow points back to A if you want. So the predecessor of B is A. That means exactly the same as saying there's an arrow from A to B. So this is what I will do at the end of this step here. I still don't know whether the distances 110 or 10 are the final ones, because B, C, and E are not on the set V of visited nodes. But I know, based on the information I have so far, this is the best I can say for these three nodes. And then at the next step, I will choose among all the distances I know already, what is the shortest for the nodes that are not already visited. Here we have two candidates, C and F. They have the same distance. So I will, through some tie-breaking rule, perhaps randomly, perhaps based on identifier, I will take one of the two. So for example, here I will add C to the visited set. So now the visited set becomes A and C. And the magic that I mentioned about OSPF, or about Dijkstra's algorithm, is that when we do this, when we add node C here, the distance C is the final distance. So there will not be a better distance. This is intuitively because C was the shortest to the visiting set, and recursively, Dijkstra shows the property that for all nodes that are in the visiting sets, the estimates of the distance are the final one. So we know the distance to C will be 10. Then I apply the same. Now I have one more node in my set, V. So I look at all the neighbors. I can have better estimates of all the neighbors of C. I have a neighbor that is B, but that gives me another estimate, 10 plus 100, 110, but this is less good, so I ignore it. I have D. D, the previous value was infinite. Now it becomes 10 plus 20, 30. So I have now a better value. I recall this better value by putting a red arrow. Same for F. F here I have, no, not same for F. For F I have another estimate, which is 20, which is less good than what I had before. So I ignore it and I don't put a red arrow. So at this time, this is the stage of the algorithm. Then we will add the next node, which is the one with the shortest distance from all the distance that we knew before. This is F. We add F here, and the same occurs. We update the distances of the immediate neighbors of F, which is only E. So E now is at a distance of 20 here. And same thing, when we do this, we know the final distance from A to F will be 10, and there will be no way to improve it on this stage. Now it's up to you to do the next step of the algorithm. If we continue from this stage, what will Dijkstra's algorithm do? So the question should be open in SpeakUp. I close the poll, and the majority says C, which is the correct answer. This is what will happen at this next step. So we will add node E, and we will update the distances. And now there is an interesting case. Node E is at a distance of 20, and node D, that was already at a distance of 30, we find also another path which has the same distance. It doesn't improve, but it has the same distance from A to C. Then with this version of Dijkstra, we keep all equal cost paths. So we will put two arrows here. We have found two equal cost paths that go from A to D, one via ACD and one via AFED. So OSPF will keep those two here. Then at step 5, after step 5, we're in this stage here, and then we will add node D. Node D has no new neighbor, so nothing happens. And then we add the remaining node, which is node B. So this is the final state. We see that in 6 iterations for a network of 6 nodes, we have completed, so it's completely deterministic number of steps in the iteration. And at the end, we have the distances and the red arrows. The red arrows are giving the paths. So if we want to compute now the path from A to D, for example, then we revert the arrows. We start from D and we find two paths here, ACD, AFED, and to E, in contrast to this node E, there is only one single path here. So we could do this. In fact, the code that is in OSPF doesn't do this because you can embed the computation of the path with the calculation of Dijkstra's algorithm, but doing that makes it more complicated to explain. So this is not what I showed, but this is what is done in the system. And at the end of this, the only thing that we distill from that is a routing table. So A will put in its routing table that in order to go to D here, there are two possible next hops, C or F. So A will write two entries in its routing table, C or F, and it will also write the cost. And this is what we will get from this computation. As I mentioned, there are stub networks. So those stub networks like N3. So this is the real network. There's a little more than just the routers here. And as I mentioned, the stub networks, which typically are many, are not computed, are not used in the shortest path computation in this Dijkstra algorithm. They're used in a second step. So after we've computed the distance to B, then we will examine all the networks that are directly attached to B and our stub, and we will add them in the routing table. For example, at A knows a path to B. Through the link state database, A knows that N3 is a stub network attached to B, so it will simply copy the routing decision that was for node B. Voila, time for a break. So we will resume at 1:15.